Welcome to G Fun Facts Online. Imagine the frantic, desperate hours following a catastrophic offshore oil spill. Emergency responders are rushing to the scene, but they are immediately forced into a grim and destructive calculus. When millions of gallons of toxic crude oil are spreading rapidly across the ocean surface, threatening fragile coastlines and marine ecosystems, containment options are agonizingly limited. One of the most effective, albeit highly controversial, methods at their disposal is in situ burning. This simply means setting the floating oil slick on fire before it has the chance to reach land. It is a blunt force solution to a highly complex environmental disaster. While in situ burning can rapidly remove vast quantities of oil from the water, it comes at a steep environmental cost. Conventional fire pools spread horizontally across the ocean surface. Because they spread out so wide, the fire actually starves its own center of oxygen. This incomplete combustion creates apocalyptic plumes of thick, black smoke, releasing massive amounts of toxic soot and greenhouse gases high into the atmosphere. Furthermore, when the fire inevitably chokes on its own lack of oxygen and dies out, it leaves behind a sticky, unburned tar mat on the ocean surface that continues to poison marine life for years. For decades, the choice has been painfully clear for responders: sacrifice the air to save the coast. But what if the chaotic, devastating power of a natural disaster could be harnessed, engineered, and unleashed to solve this exact problem? Welcome to the bleeding edge of combustion dynamics, where researchers are currently engineering massive, spinning columns of flame, essentially fire tornadoes, to act as hyper-efficient, ocean-cleaning incinerators. By manipulating the fluid mechanics of fire whirls, scientists have discovered a way to burn oil spills significantly faster, dramatically reduce toxic soot, and consume nearly all of the spilled fuel. It is a revolutionary approach that transforms a terrifying natural phenomenon into a precision tool for environmental remediation. To understand the genius behind engineering fire tornadoes for environmental cleanup, we first need to understand the beast in its natural habitat. In the wild, fire whirls, which are often referred to as fire devils or fire tornadoes, are apocalyptic forces of nature. They occur spontaneously during intense wildfires or urban conflagrations when rising heat, known as thermal updrafts, collides with turbulent, converging winds. The resulting vortex acts exactly like a chimney. As the column of air begins to spin, it creates a powerful, low-pressure core that violently sucks in additional oxygen and fuel from the surrounding environment. This spinning motion acts like a natural turbocharger. The extreme inflow of oxygen forces the fire to burn at ferociously high temperatures, stretching the flames vertically into a tight, rotating pillar. In the wild, these phenomena are uncontrollable disasters, capable of uprooting trees, hurling burning debris for miles, and generating hurricane-force wind speeds. Yet, within this chaotic devastation lies a tantalizing mechanical advantage: pure efficiency. Because the vortex constantly pulls fresh oxygen into the core of the flame, a fire whirl combusts fuel far more completely than a flat, open-air pool fire. The inspiration to harness this incredible efficiency struck Dr. Elaine Oron, a prominent aerospace engineering professor, after a freak accident in 2003. A lightning strike hit a Jim Beam bourbon warehouse in Kentucky, igniting a massive cache of alcohol. Approximately 800,000 gallons of flaming bourbon spilled into a nearby lake, triggering the spontaneous formation of towering fire whirls that literally danced across the water's surface. Observing the footage of this event, researchers noted a fascinating phenomenon. The larger fire whirls were actively pulling in and absorbing smaller ones, consuming the spilled fuel with terrifying speed. The question naturally arose: could this destructive force be tamed and put to work? The journey from observing a bourbon-fueled fire tornado to engineering a tool for marine conservation led to a serendipitous and groundbreaking discovery in a laboratory at the University of Maryland. In 2016, a team of researchers, including Dr. Oron, Dr. Michael Gollner, and Dr. Wawa Shao, were experimenting with small-scale fire whirls over water to study their potential for oil spill cleanup. Using a laboratory setup that included a pan of water layered with liquid fuel, specifically N-heptane, and a pair of offset quartz half-cylinders designed to channel air into a vortex, the scientists ignited a conventional, chaotic yellow pool fire. As the offset cylinders drew in air tangentially, the yellow flames coalesced into a turbulent, twisting fire whirl. Then, something entirely unprecedented happened. The loud, violently twisting yellow fire tornado began to shrink and stabilize. The chaotic turbulence simply vanished, replaced by an eerie silence. The towering yellow flames collapsed into a tiny, vigorously spinning bright blue flame shaped like a spinning top or an inverted cone. The researchers had accidentally discovered a completely new state of combustion, which they dubbed the Blue Whirl. Now, in the world of combustion physics, color is absolutely everything. The bright yellow and orange colors of typical campfires, wildfires, and oil burns are essentially the visible glow of pollution. Those colors are generated by black-body radiation from glowing, unburned soot particles, which is a clear indicator that the fire lacks the oxygen required to fully combust the fuel. A blue flame, on the other hand, indicates complete, soot-free combustion. The blue and violet hues are caused by the chemiluminescence of excited molecular species, such as C2, CH, and OH radicals. These molecules only emit that beautiful blue light when fuel and oxygen are perfectly mixed. By forcing the fire to spin over a liquid boundary, the researchers had triggered a fluid dynamic anomaly that allowed the fire to burn with virtually zero emissions. The discovery of the Blue Whirl sent shockwaves through the physics and engineering communities. However, creating a 3-inch flame in a controlled laboratory was only the first step. Scientists needed to understand exactly why it happened, if they ever hoped to scale it up for real-world oil spills. The answer lay in the highly complex realm of advanced fluid dynamics and required the immense processing power of supercomputers to unravel. Researchers utilized massive computational simulations to peer inside the invisible structures of the Blue Whirl, uncovering a mesmerizing interplay of airflow and chemistry. They discovered that the transition from a towering yellow fire whirl to a quiet blue one is governed by a fluid instability known as vortex breakdown. In a traditional fire whirl, the gases spin upward in what fluid dynamicists call a spiral mode. But as the swirl intensity increases, the flow suddenly collapses into a bubble mode. The fast-moving air recirculates upon itself, creating a trapped, spinning bubble of localized pressure. You can actually observe similar vortex breakdowns in the swirling vortices shedding off the wings of fighter jets during high-speed maneuvers. Within this swirling bubble of air, the supercomputer simulations revealed an absolute masterpiece of combustion architecture. The Blue Whirl is not a single flame, but rather a complex ecosystem of 3 distinct flames seamlessly operating together. First, you have the rich premixed flame. This is located at the bottom, where vaporized fuel actively mixes with incoming air, but where fuel still outnumbers oxygen molecules. Second, you have the lean premixed flame. This is located on the outer edges, where there is an excess of oxygen compared to the fuel. Finally, you have the diffusion flame. This is a purplish, hat-shaped flame crowning the top, where unburned fuel from the inside finally meets the outside air. These 3 distinct flames converge at a singular, perfectly balanced intersection known as a triple flame, which manifests visually as a brilliantly glowing, whirling blue ring. The intense recirculation of the bubble mode forces the fuel and oxygen to mix rapidly and thoroughly before they ever reach the combustion zone. This aggressive premixing ensures that every single hydrocarbon molecule is entirely obliterated, leaving absolutely no carbon behind to form soot. While the Blue Whirl represented a holy grail of clean combustion, generating it required highly specific laboratory conditions at a very small scale. An oil spill in the Gulf of Mexico obviously cannot be cleaned up by a 3-inch flame. The world needed to know if the physics of vortex-enhanced combustion could be scaled up to handle the immense, violent, and open-air conditions of a marine disaster. In February 2026, researchers provided a definitive and spectacular answer to that question. Funded by the Bureau of Safety and Environmental Enforcement, a collaborative team led by Dr. Elaine Oran and Dr. Qingsheng Wang from Texas A&M University, alongside Dr. Michael Gollner from the University of California, Berkeley, successfully engineered the world's first large-scale fire whirl for oil spill remediation. Moving out of the laboratory and into the sprawling Texas A&M Engineering Extension Service Brayton Fire Training Field, the team constructed a massive, 16-foot-tall, 3-walled triangular structure. Inside this towering structure lay a large basin of water, heavily coated in thick crude oil. When the slick was ignited, the towering offset walls forced the drafting ambient air into a vicious rotational pattern. The flames roared upward, quickly transitioning from a sluggish, smoky pool fire into a spectacular, stable, spinning vortex of fire that towered 17 feet into the air. The performance metrics of this manufactured fire tornado, which were recently published in the scientific journal Fuel, completely shattered expectations and fundamentally rewrote the rules of disaster response. First, let's look at the supercharged speed. The vortex acts like a giant incinerator, feeding oxygen to the fire at such an accelerated rate that the crude oil burned nearly 40% faster than it would in a conventional in situ fire. In the critical window of an oil spill, where every single hour dictates how much coastline will be devastated, a 40% reduction in cleanup time is an absolute game changer. Next is the radical emission reduction. By drastically improving the oxygen mixture within the core, the 17-foot fire whirl slashed the production of toxic soot by an astonishing 40%. It effectively destroyed the particulates that normally form thick, choking smoke plumes, promising significantly cleaner air for response crews and vulnerable coastal communities. And finally, near total consumption. Traditional burns always leave behind a thick, toxic sludge, but the intense, localized heat of the fire whirl achieved an astonishing fuel consumption efficiency of up to 95%. The extreme temperatures vaporized the crude oil almost entirely, preventing the formation of residual tar mats on the ocean surface. The Texas A&M experiment proved beyond a shadow of a doubt that engineering fire tornadoes for massive environmental cleanups is physically possible and overwhelmingly effective. However, transitioning this technology from a static testing facility in Texas to the rolling, unpredictable swells of the open ocean represents the next great frontier in offshore engineering. In the experiment, the fire whirl was coaxed into existence using heavy, 16-foot stationary metal walls. In the middle of the North Sea or the Gulf of Mexico, erecting giant metal walls over a moving oil slick is logistically impossible. The ocean is a dynamic, hostile environment plagued by high winds, rogue waves, and shifting currents. Fire whirls are inherently temperamental. If the ocean wind blows too hard across the top of the vortex, the delicate fluid dynamic bubble collapses, and the tornado instantly reverts back into a dirty, smoky pool fire. Consequently, the current focus of marine engineers and fluid dynamicists is the rapid development of deployable, floating structures capable of shaping airflow in open water. Future remediation frameworks may involve autonomous, heat-resistant floating baffles or specialized fire booms that can be rapidly towed around a slick by response vessels. These floating structures would be hydrodynamically designed to not only corral the oil, but also feature precisely engineered air intake slits. As the ambient ocean breeze flows through these baffles, the air would be mathematically redirected to initiate and sustain the rotational vortex required to spawn a fire whirl. Another incredibly promising avenue of research involves active air injection. Rather than relying on passive walls to catch the wind, specialized responder drones or heavily modified hovercraft could inject highly targeted streams of forced air directly into a burning slick. By artificially inducing the vortex breakdown, they could spin the fire into a tornado on command. Achieving consistent remote control of these massive thermal dynamics will be the critical hurdle before fire whirls become a standard integrated protocol in global spill response frameworks. But the story doesn't end in the ocean. While the immediate application of this technology aims to save marine ecosystems, the implications of understanding and controlling fire whirls extend far beyond oceanography. The fundamental physics of vortex-enhanced combustion, unraveled by these experiments, are currently triggering a massive paradigm shift across multiple major industries. Take fuel-flexible power generation, for example. The soot-free nature of the Blue Whirl has vast implications for global energy production. The world still relies heavily on liquid hydrocarbon fuels, but extracting energy from them cleanly is notoriously difficult. Researchers have successfully induced the Blue Whirl state using a wide variety of fuels, including N-heptane, noctane, ethanol, and even raw, unrefined crude oil. Because the vortex mechanism relies much more on fluid dynamics than specific chemical kinetics, it effectively bypasses the need for complex pre-vaporization or atomization of the fuel. This could soon lead to the development of highly efficient, fuel-flexible industrial burners and power generators that can extract maximum thermal energy from low-grade or contaminated fuels with near-zero particulate pollution. Another critical application is wildfire prediction and management. On land, fire whirls remain deadly, unpredictable adversaries. By reverse engineering how fire tornadoes form, stabilize, and collapse in the laboratory, scientists are providing wildland firefighters with unprecedented predictive models. Understanding the exact thresholds of wind shear, thermal updraft, and boundary layer interference required to trigger a fire whirl allows meteorologists to better predict when and where these deadly phenomena might spawn during a massive forest fire. This advanced warning capability has the potential to save the lives of countless frontline responders. For decades, human industry has viewed fire as a primitive, untamable force. It has been seen as a destructive element to be suppressed, or at best, utilized as a blunt instrument of last resort. The approach to massive ecological disasters like oil spills has always been defined by choosing the lesser of two immense evils. But through a brilliant synthesis of serendipitous discovery, advanced supercomputing, and bold large-scale engineering, the narrative is officially changing. By decoding the fluid dynamics of vortex breakdown and mapping the complex architecture of triple flames, science is finally learning to harness the chaotic, violent nature of the fire tornado. The transition from a terrifying, uncontrollable monster to a quiet, pure blue flame, and eventually to a precisely engineered 17-foot incinerator, proves that even the most chaotic forces of nature can be bent toward restoration. As engineers continue to refine deployable oceanic airflow structures, the frantic, smoky, and highly toxic oil spill cleanups of the past may soon be entirely replaced. In their stead, response crews will deploy perfectly controlled, towering pillars of spinning flame. These engineered tornadoes will burn hotter, act faster, and breathe cleaner air back into the sky, all while leaving the oceans pristine below. Thank you for joining us on Fun Facts Online to explore this incredible leap in environmental engineering.